I mean, you said that you can be both the hedgehog and the fox, depending on the context,
Yeah.
depending on the collaboration. So, what can you, if it's at all possible, speak to the difference between those two ways of thinking about a problem? Say you're encountering a new problem, searching for the connections versus like very singular focus.
I'm much more comfortable with the fox paradigm. Yeah. So yeah, I like looking for analogies, narratives. I spend a lot of time, if there's a result, I see it in one field, and I like the result, it's a cool result, but I don't like the proof. Like, it uses types of mathematics that I'm not super familiar with.
Yes.
I often try to reprove it myself using the tools that I favor. Often my proof is worse, but by the exercise of doing so, I can say, oh, now I can see what the other proof was trying to do. And from that, I can get some understanding of the tools that are used in that field. So it's very exploratory, very doing crazy things in crazy fields, and like reinventing the wheel a lot. Yeah. Whereas the hedgehog style is, I think, much more scholarly. You're very knowledge based. You stay up to speed on like all the developments in this field. You know all the history. You have a very good understanding of exactly the strengths and weaknesses of each particular technique. I think you'd rely a lot more on sort of calculation than sort of trying to find narratives. So yeah, I mean, I can do that too, but there are other people who are extremely good at that.
Let's step back and maybe look at the a bit of a romanticized version of mathematics.
Mm-hmm.
So, I think you've said that early on in your life, math was more like a puzzle-solving activity when you were young. When did you first encounter a problem or proof where you realized math can have a kind of elegance and beauty to it?
That's a good question. When I came to graduate school in Princeton, so John Conway was there at the time. He passed away a few years ago. But I remember one of the very first research talks I went to was a talk by Conway on what he called extreme proof. So Conway just had this amazing way of thinking about all kinds of things in a way that you wouldn't normally think of. So he thought of proofs themselves as occupying some sort of space. So if you want to prove something, let's say that there's infinitely many primes. Okay, you have all different proofs, but you could rank them in different axes. Like some proofs are elegant, some proofs are long, some proofs are elementary, and so forth. And so there's this cloud. So the space of all proofs itself has some sort of shape. And so he was interested in extreme points of this shape. Like, out of all these proofs, what's the one that is the shortest at the expense of everything else, or the most elementary, or whatever? And so he gave some examples of well-known theorems, and then he would give what he thought was the extreme proof in these different aspects. And I just found that really eye-opening. That it's not just getting a proof for a result was interesting, but once you have that proof, trying to optimize it in various ways. That proof proving itself had some craftsmanship to it. It certainly informed my writing style. That like when you do your math assignments and as an undergraduate, your homework and so forth, you're sort of encouraged to just write down any proof that works. Okay, and hand it in and get as long as it gets a tick mark, you move on. But if you want your results to actually be influential and be read by people, it can't just be correct. It should also be a pleasure to read. Motivated, be adaptable to generalize to other things. It's the same in many other disciplines, like coding. There's a lot of analogies between math and coding. I like analogies, if you haven't noticed. Like you can code something, spaghetti code that works for a certain task, and it's quick and dirty, and it works. But there's lots of good principles for writing code well, so that other people can use it, build upon it, and so on, and has fewer bugs and whatever. And there's similar things with mathematics. So
yeah, first of all, there's so many beautiful things there, and Conway is one of the great minds in mathematics ever and computer science. Just even considering the space of proofs,
yeah,
and saying, okay, what does this space look like, and what are the extremes? Like you mentioned, coding as an analogy is interesting because there's also this activity called code golf.
Oh yeah.
Which I also find beautiful and fun, where people use different programming languages to try to write the shortest possible program that accomplishes a particular task.
Yeah.
Then I believe there's even competitions on this.
Yeah.
And it's also a nice way to stress test not just the sort of the programs, or in this case the proofs, but also the different languages. Maybe that's a different notation or whatever to use to accomplish a different task.
Yeah, you learn a lot. I mean, it may seem like a frivolous exercise, but it can generate all these insights, which if you didn't have this artificial objective to pursue, you might not see.
What to you is the most beautiful or elegant equation in mathematics? I mean, one of the things that people often look to in beauty is the simplicity. So if you look at E equals mc squared, so when a few concepts come together, that's why the Euler identity is often considered the most beautiful equation in mathematics. Do you find beauty in that one, in the Euler identity?
Yeah, well, as I said, I mean, what I find most appealing is connections between different things that so if you e to the pi I equals -1. So yeah, people are, this uses all the fundamental constants. Okay, that's I mean that's cute. But to me, so the exponential function was introduced by Euler to measure exponential growth. So compound interest or decay, anything which is continuously growing, continuously decreasing, growth and decay or dilation or contraction is modeled by the exponential function. Whereas pi comes around from circles and rotation. Right? If you want to rotate a needle, for example, 180 degrees, you need to rotate by pi radians. And I, complex numbers, represents the swapping between real and imaginary axes of a 90-degree rotation, so a change in direction. So the exponential function represents growth and decay in the direction that you already are. When you stick an I in the exponential, it's instead of motion in the same direction as your current position, it's motion at right angles to your current position, so rotation. And then so e to the pi I equals -1 tells you that if you rotate for time pi, you end up at the other direction. So it unifies geometry through dilation and exponential growth, dynamics, through this act of complexification, rotation by I. So it connects together all these towards mathematics. Dynamics, geometry, and complex and the complex numbers. They're all considered they're all next door neighbors in mathematics because of this identity.
Do you think the thing you mentioned is cute? The collision of notations from these disparate fields is just a frivolous side effect, or do you think there is legitimate value in when the notation, our old friends come together and unite?
Well, it's confirmation that you have the right concepts. So when you first study anything, you have to measure things and give them names. And initially, sometimes because your model is again too far off from reality, you give the wrong things the best names, and you only find out later what's really important.
Physicists can do this sometimes. I mean, but it turns out okay.
So actually, with physics, so E equals mc squared. Okay, so one of the big things was the E. Right? So when Aristotle first came up with his laws of motion, and then Galileo and Newton and so forth, they saw the things they could measure. They could measure mass and acceleration and force and so forth. And so Newtonian mechanics, for example, F equals ma was the famous Newton's second law of motion. So those were the primary objects. So they gave them the central billing in the theory. It was only later, after people started analyzing these equations, that there always seemed to be these quantities that were conserved. So in particular, momentum and energy. And it's not obvious that things have an energy. It's not something you can directly measure the same way you can measure mass and velocity, so forth. But over time, people realized that this was actually a really fundamental concept. Hamilton eventually in the 19th century reformulated Newton's laws of physics into what's called Hamiltonian mechanics, where the energy, which is now called the Hamiltonian, was the dominant object. Once you know how to measure the Hamiltonian of any system, you can describe completely the dynamics, like what happens to all the states. Like it really was a central actor, which was not obvious initially. And this helped actually, this change of perspective really helped when quantum mechanics came along, because the early physicists who studied quantum mechanics, they had a lot of trouble trying to adapt their Newtonian thinking, because everything was a particle and so forth, to quantum mechanics, because everything was a wave. It just looked really, really weird. Like you ask, what is the quantum version of F equals ma? And it's really, really hard to give an answer to that. But it turns out that the Hamiltonian, which was so secretly behind the scenes in classical mechanics, also is the key object in quantum mechanics. That there's also an object called a Hamiltonian. It's a different type of object. It's what's called an operator rather than a function. But again, once you specify it, you specify the entire dynamics. So there's something called Schrodinger's equation that tells you exactly how quantum systems evolve once you have the Hamiltonian. So side by side, they look completely different objects. Like so one involves particles, one involves waves, and so forth. But with this centrality, you could start actually transferring a lot of intuition and facts from classical mechanics to quantum mechanics. So, for example, in classical mechanics, there's this thing called Noether's theorem. Every time there's a symmetry in a physical system, there is a conservation law. So the laws of physics are translation invariant. Like if I move 10 steps to the left, I experience the same laws of physics as if I was here. And that corresponds to conservation momentum. If I turn around by some angle, again, I experience the same laws of physics. This corresponds to conservation of angular momentum. If I wait for 10 minutes, I still have the same laws of physics. So there's time translation invariance. This corresponds to the law of conservation of energy. So there's this fundamental connection between symmetry and conservation. And that's also true in quantum mechanics, even though the equations are completely different. But because they're both coming from the Hamiltonian controls everything. Every time the Hamiltonian has a symmetry, the equations will have a conservation law. So it's once you have the right language, it actually makes things a lot cleaner. One of the problems why we can't unify quantum mechanics and general relativity yet, we haven't figured out what the fundamental objects are. Like, for example, we have to give up the notion of space and time being these almost Euclidean type spaces, and it has to be, we kind of know that at very tiny scales, there's going to be quantum fluctuations. There's a space-time foam, and trying to use Cartesian coordinates x, y, z is going to be it's a non-starter. But we don't know what to replace it with. We don't actually have the mathematical concepts. The analog of the Hamiltonian that sort of organized everything.
Does your gut say that there is a theory of everything? So this is even possible to unify, to find this language that unifies general relativity and quantum mechanics?
I believe so. I mean, the history of physics has been that of unification, much like mathematics over the years. Electricity and magnetism were separate theories, and then Maxwell unified them. Newton unified the motions of the heavens with the motions of objects on the earth and so forth. So it should happen. It's just that again, to go back to this model of the observations and theory, part of our problem is that physics is a victim of its own success. That our two big theories of physics, general relativity and quantum mechanics, are so good now, is that together they cover 99.9% of sort of all the observations we can make. And you have to either go to extremely insane particle accelerations or the early universe or things that are really hard to measure in order to get any deviation from either of these two theories to the point where you can actually figure out how to combine them together. But I have faith that we've been doing this for centuries. We've made progress before. There's no reason why we should stop.
Do you think you will be a mathematician that develops a theory of everything?
What often happens is that when the physicists need some theory of mathematics, there's often some precursor that the mathematicians worked out earlier. So when Einstein started realizing that space was curved, he went to some mathematician and asked, is there some theory of curved space that the mathematicians already came up with that could be useful? And he said, oh yeah, there's, I think Riemann came up with something. And so, yeah, Riemann had developed Riemannian geometry, which is precisely, a theory of spaces that are curved in various general ways, which turned out to be almost exactly what was needed for Einstein's theory. This is going back to Wigner's unreasonable effectiveness of mathematics. I think the theories that work well to explain the universe tend to also involve the same mathematical objects that work well to solve mathematical problems. Ultimately, they're just sort of both ways of organizing data in useful ways.
It just feels like you might need to go some weird land that's very hard to intuit. Like, you have like string theory.
Yeah, that was a leading candidate for many decades. I think it's slowly falling out of fashion because it's not matching experiment.
So one of the big challenges, of course, like you said, is experiment is very tough.
Yes,
because of how effective
both
theories are. But the other is like, just, you're talking about, you're not just deviating from space-time. You're going into like some crazy number of dimensions. You're doing all kinds of weird stuff that to us, we've gone so far from this flat Earth that we started at, like you mentioned. Now we're just, it's very hard to use our limited ape descendants of cognition to intuit what that reality really is like.
This is why analogies are so important. The round Earth is not intuitive because we're stuck on it. But round objects in general, we have pretty good intuition over. And we have intuition about light works and so forth. And like it's actually a good exercise to actually work out how eclipses and phases of the sun and the moon and so forth can be really easily explained by round Earth and round moon, and models. And you can just take a basketball and a golf ball and a light source and actually do these things yourself. So the intuition is there, but you have to transfer it.
That is a big leap intellectually for us to go from flat to round Earth, because our life is mostly lived in flatland.
Yeah.
To load that information, and we're all like take it for granted. We take so many things for granted because science has established a lot of evidence for this kind of thing. But we're on a round rock.
Yeah.
Flying through space.
Yeah.
That's a big leap, and you have to take a chain of those leaps the more and more and more we progress.
Right. Yeah. So modern science is maybe again a victim of its own success. Is that in order to be more accurate, it has to move further and further away from your initial intuition. And so, for someone who hasn't gone through the whole process of science education, it looks more and more suspicious because of that. So we need more grounding. I mean, I think there are scientists who do excellent outreach, but there's lots of science things that you can do at home. There's lots of YouTube videos. I did a YouTube video recently with Grant Sanderson. We talked about this earlier. That how the ancient Greeks were able to measure things like the distance to the moon, distance to the Earth, and using techniques that you could also replicate yourself. It doesn't all have to be like fancy space telescopes and very intimidating mathematics.
Yeah, that's. I highly recommend that. I believe you give a lecture, and you also did an incredible video with Grant. It's a beautiful experience to try to put yourself in the mind of a person from that time, shrouded in mystery.
Right.
You're like on this planet. You don't know the shape of it, the size of it. You see some stars, you see some things, and you try to like localize yourself in this world. And try to make some kind of general statements about distance to places.
Change of perspective is really important. You say travel broadens the mind. This is intellectual travel. Put yourself in the mind of the ancient Greeks or some other person, some other time period. Make hypotheses, spherical cows, whatever. Speculate. And this is what mathematicians do, and some sort of artists do. Actually,
it's just incredible that, given the extreme constraints, you could still say very powerful things. That's why it's inspiring. Looking back in history, how much can be figured out
right
when you don't have much. to figure out stuff
if you
with.
propose axioms, then the mathematics lets you, follow those axioms to their conclusions, and sometimes you can get quite a long way from initial hypotheses.
If we can stay in the land of the weird, you mentioned general relativity. You've you've contributed to the mathematical understanding of Einstein's field equations. Can you explain this work? And from a sort of mathematical standpoint, what aspects of general relativity are intriguing to you, challenging to you?
I have worked on some equations. There's something called the wave maps equation, or the sigma field model, which is not quite the equation of space-time gravity itself, but of certain fields that might exist on top of space-time. So Einstein's equation of relativity just describes space and time itself. But then there's other fields that live on top of that. There's the electromagnetic field, there's things called Yang-Mills fields, and there's this whole hierarchy of different equations, of which Einstein is considered one of the most nonlinear and difficult. But relatively low on the hierarchy was this thing called the wave maps equation. So it's a wave which at any given point is fixed to be like on a sphere. So I can think of a bunch of arrows in space and time, and the arrows are pointing in different directions. But they propagate like waves. If you wiggle an arrow, it will propagate and make all the arrows move kind of like sheaves of wheat in the wheat field. And I was interested in the global regularity problem again for this question. Like, is it possible for all the energy here to collect at a point? So the equation I considered was actually what's called a critical equation, where it's actually the behavior at all scales is roughly the same. And I was able barely to show that that you couldn't actually force a scenario where all the energy concentrated at one point, that the energy had to disperse a little bit, and the moment it dispersed a little bit, it would stay regular. Yeah, this was back in 2000. That was part of why I got interested in Navier-Stokes afterwards, actually. Yeah, so I developed some techniques to solve that problem. So part of it is this problem is really nonlinear because of the curvature of the sphere. There was a certain nonlinear effect which was a non-perturbative effect. It was when you sort of looked at it normally, it looked larger than the linear effects of the wave equation, and so it was hard to keep things under control, even when the energy was small. But I developed what's called a gauge transformation. So the equation is kind of like an evolution of sheaves of wheat, and they're all bending back and forth, and so there's a lot of motion. But like if you imagine like stabilizing the flow by attaching little cameras at different points in space, which are trying to move in a way that captures most of the motion. And under this sort of stabilized flow, the flow becomes a lot more linear. I discovered a way to transform the equation to reduce the amount of nonlinear effects, and then I was able to solve the equation. I found this transformation while visiting my aunt in Australia, and I was trying to understand the dynamics of all these fields, and I couldn't do it with pen and paper, and I had not enough facility of computers to do any computer simulations. So I ended up closing my eyes, being on the floor, and just imagining myself to actually be this vector field and rolling around to try to see how to change coordinates in such a way that somehow things in all directions would behave in a reasonably linear fashion. And my aunt walked in on me while I was doing that, and she was asking, "What am I doing this?"
It's complicated, is the
yeah,
answer.
yeah, and she said, "Okay, fine. You're a young man. I don't ask questions."
I have to ask about the, how do you approach solving difficult problems? What, if it's possible to go inside your mind when you're thinking, are you visualizing in your mind the mathematical objects, symbols maybe? What are you visualizing in your mind usually when you're thinking?
A lot of pen and paper. One thing you pick up as a mathematician is sort of, I call it cheating strategically. So the beauty of mathematics is that you get to change the problem, change the rules as you wish. Like this, you don't get to do this for any other field. Like if you're an engineer and someone says build a bridge over this river, you can't say I want to build this bridge over here instead, or I want to build it out of paper instead of steel. But a mathematician, you can do whatever you want. It's like trying to solve a computer game where there's unlimited cheat code is available, and so you can set this. There's a dimension that's too large. I'll set it to 1. I'd solve the one-dimensional problem first. Or there's a main term and an error term. I'm going to make a spherical cow assumption. I'll assume the error term is 0. And so the way you should solve these problems is not in sort of this Iron Man mode where you make things maximally difficult, but actually the way you should approach any reasonable math problem is that if there are 10 things that are making your life difficult, find a version of the problem that turns off 9 of the difficulties but only keeps 1 of them, and solve that. And then that just figures, so you install 9 cheats. Okay, if you install 10 cheats, then the game is trivial. But you install 9 cheats, you solve 1 problem, that teaches you how to deal with that particular difficulty. And then you turn that one off and you turn something else on, and then you solve that one. And after you know how to solve the 10 problems, 10 difficulties separately, then you have to start merging them a few at a time. As a kid, I watched a lot of these Hong Kong action movies from my culture. And one thing is that every time there's a fight scene, so maybe the hero gets swarmed by 100 bad guy goons or whatever. But it'll always be choreographed so that you'd always be only fighting one person at a time. And then it would defeat that person and move on. And because of that, he could defeat all of them, right? But whereas if they had fought a bit more intelligently, and just swarmed the guy at once, it would make for much worse cinema. But they would win.
Are you usually pen and paper? Are you working with computer and LaTeX?
I'm mostly pen and paper, actually. So in my office, I have 4 giant blackboards, and sometimes I just have to write everything I know about the problem on the 4 blackboards and then sit on my couch and just sort of see the whole thing.
Is it all symbols like notation, or is there some drawings?
Oh, there's a lot of drawing and a lot of bespoke doodles that only make sense to me. I mean, and the beauty of a blackboard is you erase, and it's a very organic thing. I'm beginning to use more and more computers, partly because AI makes it much easier to do simple coding things. That if I wanted to plot a function before, which is moderately complicated, has some iteration or something, I'd had to remember how to set up a Python program and how does a for loop work and debug it, and it would take 2 hours and so forth. And now I can do it in 10-15 minutes. It's much, I'm using more and more computers to do simple explorations.
Let's talk about AI a little bit if we could. So maybe a good entry point is just talking about computer-assisted proofs in general. Can you describe the lean formal proof programming language and how it can help as a proof assistant, and maybe how you started using it and how it has helped you?
So Lean is a computer language, much like sort of standard languages like Python and C and so forth, except that in most languages, the focus is on producing executable code. Lines of code do things. They flip bits, or they make a robot move, or they deliver you text on the internet or something. So Lean is a language that can also do that. It can also be run as a standard traditional language, but it can also produce certificates. So a software language like Python might do a computation and give you that the answer is 7. Okay, that it does the sum of 3 plus 4 is equal to 7. But Lean can produce not just the answer, but a proof that how it got the answer of 7 as 3 plus 4, and all the steps involved so it creates these more complicated objects, not just statements, but statements with proofs attached to them. And every line of code is just a way of piecing together previous statements to create new ones. So the idea is not new. These things are called proof assistants, and so they provide languages for which you can create quite complicated, intricate mathematical proofs, and they produce these certificates that give a 100% guarantee that your arguments are correct if you trust the compiler of Lean. But they made the compiler really small, and there are several different compilers available for the same
Can you give people some intuition about the difference between writing on pen and paper versus using Lean programming language? How hard is it to formalize statement.
So Lean, a lot of mathematicians were involved in the design of Lean. So it's designed so that individual lines of code resemble individual lines in a mathematical argument. Like you might want to introduce a variable, you want to prove by contradiction. There are various standard things that you can do, and it's written so ideally it should be like a one-to-one correspondence. In practice, it isn't, because Lean is like explaining a proof to an extremely pedantic colleague who will point out, okay, did you really mean this? Like, what happens if this is 0? Okay, how did you justify this? So Lean has a lot of automation in it to try to be less annoying. So, for example, every mathematical object has to come with a type. Like if I talk about x, is x a real number or a natural number or a function or something? If you write things informally, it's often in terms of context. You say, clearly x is equal to, let x be the sum of y and z, and y and z were already real numbers, so x should also be a real number. So Lean can do a lot of that, but every so often it says, wait a minute, can you tell me more about what this object is, what type of object it is? You have to think more at a philosophical level, not just sort of the computations that you're doing, but sort of what each object actually is. In some sense.
Is it using something like LLMs to do the type inference, or like you mentioned with the real number?
It's using much more traditional, what's called good old-fashioned AI. You can represent all these things as trees, and there's always algorithms to match one tree to another tree.
So it's actually doable to figure out if something is